Okay, so I'm starting over again and to finish up the lines and planes lecture. Where we left off was here, and I was just talking about the equation of a plane. And we remembered that previously, over in the upper left, we said that an equation of a plane could be ax plus by plus cz. So this is kind of like the three slopes equals d, some constant. And then we took a more vector-based approach. We started with a normal vector, and we dotted the normal vector with some vector that's in the plane, p0 being some point we know, and then p being some arbitrary point, x, y, z. And so when we go through a bunch of algebra, we discover that if we set this equal to 0, we get a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And then what I did is I took all the ax zeros, so it's ax0, by0, cz0, moved them over to the other side and called that d, and it looked like this. All right, so we have 3 points, 3 intercept type of points in our coordinate system that helps us make a plane. And this is kind of important to remember how we find this for the next few sections. And there's not that much left, really, in this section, so this won't be a very long lecture at all. The next one we want to get is the let's see, the line of intersection. In black again, line of intersection between two planes. Okay, well, if a line is, let's say we have plane A, and then over here I've got plane B. Well, I know that any line in plane A is perpendicular to this normal vector A. Normal, that could be a normal vector A, or it doesn't have to be a unit vector, right? And I know that any line in B is perpendicular to, again, the normal vector in B. So how does that help us? If there's only one line of intersection that lies in both planes, and B. So here's a line that lies in both planes, which is, the intersection of two lines is a point, the intersection of two planes is a line. So, okay, that's Walter. Give me just a second. I'm going to pause. I'll be right back. Okay, where were we here? Sorry about that. Lines of intersection between two planes. Plane A, any line in A is perpendicular to the normal. Any line in B is perpendicular to the normal of B. Only lines of intersection. Then we got to crying baby, poop, clean diaper, more poop, another clean diaper, and we're back here. All right, so we're looking for the line of intersection, right? And the line of intersection has to be in both planes. Not only does it have to be in both planes, but it has to be perpendicular to the normal vector of both planes. Well, perpendicular to two normal vectors, so it must be that the line of intersection is perpendicular to NA and NB, well, what's a vector parallel to NA and NB? So the cross product. So NA crossed with NB is perpendicular to both. Hence, parallel to the line of intersection. So are we done? No, we're not quite done yet. We now have a vector, NA cross NB is perpendicular to NA cross NB is some third vector that is perpendicular to both of these. Therefore, it must be parallel to the line of intersection, but is not necessarily the line of intersection. So we need to find some point that is in both planes and affix our new parallel vector. So how do we do that? Well, I could say that my plane A again, let's say, is AX plus BY plus CZ equals D. And I could say that plane B is, let's see, where do we have to start? I don't know how this is going to work out, but EX, EF, Y plus GZ, EFGH equals H. Well, what I can do, I know that this line of intersection between the two planes, and this is very hard to do without being able to like move my arms around. The line of intersection between two planes has to cross the plane z equals 0. Since it goes infinitely in both directions, it must cross z equals 0. Right? So now I can say AX plus BY equals D, and I can say that EX plus FY equals H, and I can solve these two, X and Y, and I can use point P, and I can get X, Y, 0. So now I have a point P to which I can attach this vector that I gave over here, NA cross NB, and then I can, using a point and a vector, now it's old news, right? We go way back to that submarine problem, and parameterize a line in 3D space. Okay, so that's the line of intersection between two planes. Next topic is the distance from a point to a plane, and this one's a little easier. From point to plane. Well, I could say that I've got this plane here, and this is a little easier to draw in 3D because there's not that much going on. And I've got some point, let's say that I'm going to call this point Q. And I'm really interested in the distance down to this plane here, right? Unfortunately, I don't know what point it is that is exactly under this point. And I say under just because it's easy to picture as being under, because the distance between the point and the plane is this perpendicular. What if I only know my point I only know my point P over here. Now we've got points P and Q, so maybe I've given away the story already. I know this, if I know points P and Q, I'm trying to be careful as I draw this, and that makes my little menu pop up. If I know points P and Q, I can make a vector P and Q. If I know my plane, I also have some vector there like that, right? Well, what is the projection of PQ onto N? What is the projection of PQ onto N? And again, I never remember this formula, so I got to figure it out. So I want the projection of PQ onto N. So I'm going to need to know this theta, and it's going to be the magnitude of PQ times the cosine of theta. Yeah, cosine of theta. I remember what that is. That has to do with the dot product. So I'm going to rewrite this as the magnitude of PQ times PQ dot N divided by the magnitude of PQ and the magnitude of N. So that gives me the cosine of the angle, and then I need to, I think that's all I need to do, isn't it? PQ dot N divided by, yeah, that's it. So I can bring out the all-powerful red. Let's see, is this right? Because cosine of theta is just that, so I need PQ dot cosine of theta. Yeah, that's it. If I wanted to make this vector, I'd have to put a unit vector in there, but I'm not going to use that. So bring out the red pen here. So my magnitude of PQ cancels out. So what does this equal out to be? It becomes PQ. This is supposed to be a dot here, by the way. So it's PQ dot normal vector over the magnitude of my normal vector. So again, it's like, what the heck? This dot product shows up everywhere. Why? Because the dot product is really a nice tool to get to the cosine of theta, right? So there's so this gives us the distance. Wait, let's check to make sure this is a scalar. Vector dot vector, vector dot vector, dot product, scalar product. Scalar divided by magnitude is still a scalar. So yeah, that makes for a good distance. So this whole thing equals distance, right? Because I needed, let's go back to the picture. I needed this thing times the cosine of this angle, which is really the same as this, which is the same as this. In fact, I'm going to draw that in there too. I'm talking myself into a lot more work than I really wanted to do for this lecture. But so this is D here, which is the same as the distance here. Okay, so that's that. So that's a great example of using the dot product as a tool to get the cosine of two angles. Well, what about I think the last one we have to do here. Boy, it's it's only 6 in the morning and I'm running out of stuff to talk about. Go back to my black pen here. What about the angle between two planes? Now this one is nearly impossible to draw, so I'm going to refer to the picture in the book, which is figure 12.42 on page 712, because I'm not going to attempt to draw. Oh, what the heck, I'll attempt to draw it. We got time. So I'm going to draw one plane that kind of goes like this. This is going to be my blue plane. Yeah, I'll do that in blue. So I've got a blue plane that kind of goes like this, but then that one is going to get hidden. And then I've got a red plane that sits underneath it that goes kind of like this. But then the red plane is on top over here, and the red plane continues to go up like this. And my blue plane, and this is exactly what I said I was going to avoid doing, right? Talking myself through these complicated drawings rather than just pausing. And then the blue plane goes like this. All right. And then we can draw this kind of dotted line here that represents the line of intersection. We've already talked about that. And I'll draw a red line in here to represent it like that. So that's the intersection of two planes. Well, I know that I could draw a blue normal vector, right, which really defines the tilt of a plane can be defined by its normal vector. We'll call that normal blue. And then I could define a red normal vector which goes off like this way. And we'll call that normal red, R. And if I want to get the angle between those two planes, well, this becomes almost obvious now. So theta, which is right here, equals, well, the dot product, right? So it's normal R dotted with normal blue divided by the magnitude of normal R times the magnitude of normal blue. So that's it. That's the angle between the two planes. So again, our old friend dot product becomes useful not necessarily just for projections, but it gets us angles too. All right, that's all I've got. I hope you have time to watch this before class, and if not, we've got time to discuss the problems on the homework. Thanks again. See you soon.